Okay, in this lesson we are going to look at the sums of arithmetic progressions. What do I mean by progressions? What does a progression refer to? Right, we talk about these as APs. The progression refers to either a sequence of numbers or a series. And what's the difference between these two? Test yourself. Sequence, some kind of ordered set of numbers that follow a pattern. Series, sum of those things. Right, so sums of arithmetic progressions really does hammer down on the series side of things. Okay, so in this section we're also going to meet sigma notation, because sigma notation is shorthand for sum of. So brilliant. Well, let's start with a little story. There was a fella in a primary classroom in old Germany back in the day, a couple hundred years ago. This fella by the name of Gauss. You may have heard of him. He did one or two things in the mathematical world. Anyway, he was a youngster and he was being a bit silly in class, and his teacher said, righto, add up the numbers from 1 to 100 and just go sit in the corner and do that, hoping that this would occupy young Gauss for some period of time. However, Gauss was a smart fella, and so he added up the numbers from 1 to 100 in a split second and shot the answer back at the teacher, who was dumbstruck. And what we're going to look at firstly is how young Gauss came up with this so fast. So what we're going to do is look at a sum of the 100 numbers that he was asked to add up. Now there they are. These are the numbers. Now this is an arithmetic progression, I'm sure you agree, as we are going up by 1 each time. So the natural numbers, the counting numbers, form an arithmetic progression. What did he do? Well, if we did a little reorder of, and this is what Gauss did, and perhaps you can work with me on this. If we reorder these into pairs, so we have a look at perhaps this pair of numbers here, 1 and 100, right? So we say, right, well, let's reorder this sum. So it's 1 plus 100, all right, and then we'll add up this number here and this number here. So we got 2 plus 99, and then we'll take this number here and this number here. And that's 3 plus 98. So what we're doing is we're just pairing them up, but we're pairing first and last, second and second last, third and third last. And the reason for that is that you will see, won't you, here that these sums all give us 101. So an arithmetic progression has this nice little feature to it, that if you take pairs, they're going to add up to the same. So pairs of numbers in an arithmetic sequence are going to give you the same result. And the simple reason for that is whatever I go up by here, I go down by here. So if I take first and last, by taking the second, I go up by 1, and the second last, I go down by 1. Now, if we generalize that, that's D. We go up by D, down by D. We have the same sum. So all Gauss had to do was work out, well, how many pairs are there? There are 100 numbers you've asked me to add up. So that means I've got 50 pairs of 101. I've got 50 of these. Okay, and 101 times 50 was no problem for a genius like Gauss, because he would just go, well, 101 times 50 is just 100 times 50 plus 1 times 50. I know what 100 times 50 is. That's 5,000. I know just add 50 to that, and here's my answer, 5,050. Did that as quick as you like. So that sets the scene for arithmetic progressions. How do we generalize this? Well, if we've just got a what do we call that first term? So what we've got here is, if we put this into some kind of pattern, is we would say that the sum of, in this case, the sum of 100 terms was equal to, well, it was 100 divided by 2, because that's how many pairs we had. That was the 50, and I multiplied that by this 1 plus 100, which is the first and the last term. So 1 plus 100. Right, so that's what it looks like. Now, if we change these numbers. Obviously, we can have different numbers of terms, and the first and last are going to change. But if I take another set of numbers, 3 plus 5 plus 7 plus 9 plus 11 plus 13, then the first and the last in this case is 3 and 13. It's 16. Right, and the 5 and the 11 is 16, and the 7 and the 9 is 16. So in this case, with my 6, I would have 6 over 2 by 3 plus 13. So this is a pattern that will work for any arithmetic progression. So to put it into a formula, which is what we all want, so we can work with any progression, the sum to n terms. Now what's this 100 represent? It represents how many terms there are. All right, we halve the number of terms, and we multiply by 1, which is our first term, and 100, which is our last term. Now, our last term is the nth term. Okay, so that's as simple as that. It's first plus the last. Now, sometimes, however, we don't know what this last term is. But we walked into this lesson knowing what un equals. Un, we have an expression for un using our first term and our common difference. And there it is there. So I can rewrite this in another way that is going to be perhaps more useful for us more often. U1 plus, now I'm going to put this U1, this UN I'm going to rewrite as U1 plus n minus 1d. And I've got myself a nice new formula. I've just got to collect some like terms here. And I've got n over 2. I've got 2u1 plus n minus 1 times d, and that's my sum to n terms of an arithmetic sequence. So we have now two sum formulas to use, that one there and that one there. So we can use either one. This one's nice and concise, isn't it? If you know what the last term is, and when you do sigma notation, you always do know what the last term is. So this one is quite good for sigma sums. This one probably not. This is more for just if you know how many terms you're taking. So let's look at some perhaps some examples now. Okay, so here's an example. Let's find the sum of the first 20 terms of this sequence here. Well, from this, right, 20 terms. So I don't know what that last term is. So which formula do you think we're going to use? I reckon it's going to be this one here, the second one. So U1 is 5, D is equal to 3, and N equals 20. I always reckon it's good to get all that info down. So the sum of 20 terms is going to be 20 over 2. Right, in we go, twice U1, so 2 times 5, plus 19, n minus 1 by 3. So we get 10 here, 10 plus 57. So you can see this is going to work out quite nicely to 670. Okay, a sigma sum example, and I think what you'll find here is that the use of the first formula is going to work for us with a sigma. I'll show you how. So I know because this is linear, I know that I have an AP. Okay, and let's just roll this out for a couple of terms. So r equals 1. All right, so this sum looks like this. 5 times 1 is 5 minus 4 is 1. That's the first term. I put r equals 2 in now, and I get plus 5 2s are 10 minus 4 is 6. I put r equals 3 in. I get 5 3s are 15 minus 4 is 11. All right, and that's enough. I just get the first 3 terms down, and then I go, good, that continues now all the way to the 28th term. I put that in. 5 times 28, that's 140 minus 4 is 136. Now, because we have our last term, we're going to use the sum to n terms equals n over 2 u1 plus un, because my u1 is right there and my un is right there. And I know that I know what n is. N's 28. I've got everything I need to answer this question. So I'm just going to put in here 28 over 2, which is 14, by 1 plus 136. So 14 times 137. which is 137 by 14. 4 sevens are 28, 14. 4 ones are 4 is 5. We've got 7 there, 3 and 1, although I needed to put in a 0. 0, 7, 3, 1. So we've got 8, 11, 9, 1, 9, 1, 8 is what I reckon. Okay, we'll just have a look at one more example, different style of question. This is in this question we're given the SN. So we're not given term information. We're given we're given what the expression is for the sum. So this tells me for any number of terms, if I want to find out the sum of the first 10, I just put that in. So this is sum information, not term information. Right, but we need some information out, but we want to know what the common difference is and the first 3 terms of the series. Well, the way to go with all of these types of questions is to just find out what S1 is, because S1 is going to be your first term, the sum of one term. That's going to give you U1. All right, so S1 is going to be U1, and that's going to be 1 by, what's that, 2 minus 3, negative 1. So my first term is negative 1. Okay, so, well, let's find out S2, because, right, if I find out the sum of 2 terms, the difference is going to be my second term. So S2 will be equal to, that's twice 1, which is 2. So if my first term is 1 and the sum of my first 2 terms is 2, if I go over here and just start to write out my sequence, I go minus 1. Now this one plus this number have to equal 2. So that number must be 3. Let's see if this works. Let's go to S3. That's equal to 3 by 3, which is 9. Now if this is working out okay, I'm at 2 at the moment. I need another 7 to make 9. Minus 1 plus 3 tubes. Yep, that looks good. And have I got a arithmetic going on here? I think I do indeed. I've got 4 there and 4 there. So it really is just a process of belting out the first few terms, so crunching them out and getting some information from it. So from this we can say that U1 is equal to negative 1, my D is equal to 4, and the world's my oyster now. I've already answered the common difference. The first 3 terms, well, I've already got them. There they are, minus 1, 3, and 7. So I think we're right to go. There are still a few different types of questions to finish exercise 1B. That'll be questions 9 through to 15, I think. So have some fun with that. I'll see you shortly.